Let's say that I had two compartments of water, and they're separated by a semi-permeable membrane. Now, what do I mean by semi-permeable membrane? That means they allow some things to go through and not other things. And let's say this semi-permeable membrane, it does allow water molecules to pass. And in a few seconds, we'll talk about what it does not allow to pass, which makes it semi-permeable. But let's just think about what would happen if we just had water molecules on either side. Well, we've already talked about it in the videos on diffusion. The water molecules, since we have an equal concentration on either side, the probability that one of these water molecules goes this way in a certain amount of time is equal to the probability that a water molecule goes from right to left in the same amount of time. And that's because we have equal concentrations, and these things are all bouncing around in all different ways. They all have different velocities. They have different speeds and in different directions, and we just have to think about it probabilistically. The probability of going from left to right through one of these gaps is going to be equal to the probability of going right to left in any given period of time. But now let's make this interesting. Let's treat our water as a solvent, and let's put some solute in it. So let's dissolve some solute. So let's throw some solute particles here, and I'm going to make them bigger so you can see they would physically have trouble passing through these gaps. There's other ways where you could have semi-permeable membranes that use charge to allow certain things to pass through and not others, but it's easier to visualize the size and thinking about the membrane as only allowing certain things of certain size to pass through. So let's throw some solute there, and actually I'll throw a little bit of solute here too. I'll do one or two particles right over here, but I'm going to do many more. I'm going to do many more over there on the right-hand side. So we have a higher concentration of solute on the right-hand side. And this is a semi-permeable membrane. And you can see even from the size where I drew these gaps, these big particles aren't going to be able to go through the membrane. They aren't going to be able to diffuse. If they were allowed to diffuse, then they would just go down their concentration gradient. And in any given moment of time, you would have a higher chance of one of these big particles moving from the right to the left than from the left to the right, because you just have more on the right-hand side. But this is a semi-permeable membrane. These things aren't just going to be allowed to naturally diffuse. Now, all of these big particles, they all have their own unique velocities. So they all have their unique velocities. What do we think is going to happen? Well, let's just think about the problem. We know that the big particles can't diffuse from one side to another, but what's going to happen to the water molecules? Well, the water molecules on the left-hand side, they're not going to be stopped. If they're bouncing in the right way, they can bounce from the left to the right, or they could move from the left to the right through one of these gaps. But what about the ones on the right side? Well, if they're the just right conditions, maybe this character could move through this. So you're definitely going to have water molecules going back and forth. But I'd argue that the ones on the right-hand side, there's a lower probability of water molecules from the right-hand side moving to the left as from the left-hand side moving to the right. And why is that? Well, there's all this interference at play from these big molecules that aren't able to diffuse. These are going to be bouncing around. Sometimes you could imagine them even blocking. They're going to be blocking the approach to these openings. If this membrane wasn't here, they wouldn't block the approach. They would just keep on going. But since that membrane is there, they might block it, or they might ricochet off. And while they ricochet off, they might push on some water molecules. Going in this direction right over there. And so an argument can be made that these water molecules, some of them will still make it from right to left, but you have a lower probability of going from right to left as you have from going to left to right. And so because of this, you would have a net inflow of water from this area where you have a low solute concentration. And remember, the solute is the thing that's dissolved in the water. And in general, we always consider the solvent to be whatever there's more of. In this case, it's water, and water is probably the most typical solvent. And the solute is whatever there's less of. So the solute is dissolved in the solvent. And so we have a net migration of the water molecules from this solution that has a low solute concentration to one that has a higher solute concentration. And this phenomenon we call osmosis. We call this osmosis. And there's other arguments for osmosis, and it's something that we've observed many, many, many times. If you put something that's used to fresh water, and it has if it has skin that is, or it has membranes that allows water to pass through it, put it in salt water. The kind of the famous things like slugs will not do well in the presence of salt, because the water inside the slug will do exactly what is happening in this diagram. Now, this mechanism that I just talked about, that the molecules that cannot pass through the membrane, blocking the water molecules from going right to left, ricocheting off and maybe causing the ones that are on the right side to maybe move in this direction when they bounce into them. That's one explanation. Another possibility is many times the solute that's being dissolved in water has some charge associated with it. So when we think of, say, regular table salt, you have sodium ions that get regular table salt is sodium chloride, but when you put it in the water, you have sodium ions and you have chloride ions, These are negative, so the chlorides are negative, the sodium ions are positive. And above and beyond doing some of the mechanical blockage that I just talked about, there's also the idea that possibly that because they are ionic, they have charge, and water has partial charges, they also might stick to more of the water. So the waters that stick to them aren't going to be available to move through the membrane. And so what do I mean by the water is going to stick to them? Well, when we think about a water molecule, it's an oxygen, and on the oxygen end you have a partially negative charge, and then you have two hydrogens. Let me write it this way. You have two hydrogens right over here. There's a partially positive charge. And so they're going to be, this oxygen end away from the hydrogens is going to be attracted to the sodium molecule. And so it's going to be less, so if the sodium molecule can't make it through, this guy's going to want to stick to the sodium molecule. And so you can kind of imagine all of these water molecules sticking to the sodium molecule, which would make it less likely that these would pass from right to left than the ones that are passing from left to right. Similarly, if you have a negatively charged ion like this, well, then you could orient the water the other way, where the partially positive charged hydrogen ends are going to be attracted to the chloride ion right over here. And since the chloride ion might not be able to get through, well, then these molecules that are stuck to it are going to be less likely to flow through. These molecules are going to be more attracted to the chloride, or more attracted to the sodium ions, than they would be to other water molecules that only have partial charges. These have full charges. So if these can't get through, well, then maybe it's a lower probability that these are going to get through as well. But the combined effects of all of these, and I'd love for any of y'all to point me to a nice simulation, or maybe we'll create one on the Khan Academy computer science program to show this, is that you're going to have a higher probability of the water molecules over here going from left to right than the water molecules over here going right to left, from mechanical blockage or these big molecules ricocheting off and pushing them in the wrong direction, or because they're just stuck to the big molecules because the big molecules are charged. And that is osmosis.